Okay, so a rectangular tube has an ultimate strength of 60 KSI. KSI, and dimensions as shown. Find A, bending moment M, such that the factor of safety is 3, and B is radius of curvature of the tube, assuming E is 10.6 times 10 raised to 6 psi. Say that again. It's the ultimate strength. So on the curve, stress strain curve, there is yield strength, and then some point there's an ultimate strength. Okay, so we can think of solving this. Well, look at it backwards. Let's try to see. We asked to solve for M, and we know that M is related to the stress by this formula. So that's an unknown. Since we're given the dimensions of the box, we can find I. We can also find Y, because that's the distance from the neutral axis where you would get maximum stress. But sigma is not given to us. Okay, so perhaps we can get sigma by knowing the factor of safety and the ultimate strength. Now, the definition for factor of safety is allowable stress divided by max stress. Now, when it comes to allowable stress, this is something which is a design parameter. You want to design it based on ultimate strength, or you want to design it based on yield strength. In this case, since you're not given anything about the yield strength, I'm going to use the allowable stress to be the ultimate strength in order to figure out the max stress, which happens to be here max, right? So this would be sigma max y max, since we are now accounting for the maximum stress in order to find the maximum moment. So the allowable stress will use ultimate strength. Max stress is sigma max, and so we can solve for sigma max. (60 divided by 3 is 20 KSI. So next we need to find the question is, where is the maximum stress occurs? It occurs where y is maximum. So y is the distance from the neutral axis for a geometry which is symmetric, like the one shown. The neutral axis should pass through the geometric center, and the geometric center, we don't really need to do any math. It's kind of obvious that the geometric center is the center. The neutral axis is passes through geometric center, which happens to be here, point C, right in the middle of the box. So then y max, so y is the distance from that, and then you will either use y max to be positive here, which will be, in this case, this will be compressive. The stress on the top layer will be compressive, and the bottom will be tensile, and that's just because the way this moment is. It's going to bend this beam in an arc which is upwards, right? So it's going to be curved like a U, and that's why the top portion is going to be compressive, the bottom is going to be tensile. So Y max is half of 5, which is 2.5. Yeah. Yes, it is. It can be negative. If you're asked to find the maximum tensile strength, then you would put Y equals negative, which will correspond to this point. Here, the design is not really based on, here we assume the compressive and normal compressive and tensile strength is the same. And so you can use either of those points. But there are situations where you want to use one over the other. So there are different things going on here. So let's see. So this M is, okay, so if you put positive, so if you put, let me just write this down slightly differently. So M, or let me put sigma equals M y divided by. So now we need to decide the sign. So I has a positive, is always positive. So depending on the sign of M and depending on the sign of Y, we can get sigma. Now in this case, if you look at the beam from this way, right, then you see that the beam is bent like this. Okay. So M is clockwise, which is negative. And so when you use this formula, you'll have sigma equals minus M. And then if you, so our convention is positive is upwards. So this will be positive Y divided by I. I put a positive here because we're trying to find the stress here. So you see that the stress comes out to be negative. Compressive. Right? And similarly, if you put Y equals negative, which is downwards, then you'll put a negative Y here on for the Y, and then net negative multiplies with the negative from M, and sigma becomes positive. And so the stress in the bottom layer is positive or tensile. So it all works out right. Right. So I think that doing it this way is a bit confusing. And so what I recommend doing is not to worry too much about the sign convention there. Just go over this and look at how it will bend, right? It will bend something like this, right? Because of this moment. And so on top, there would be compression, and bottom, there will be tension. So the stress here will be negative, stress here will be positive. That's probably easier than doing what I did here, which is also, by the way, it's more gratifying because then it's just what I've written down is independent of me fudging the signs. It just comes out from the sign convention we use. Clockwise is positive, negative, and counterclockwise positive for the moment. Okay, so Y max is in this case 2.5 inch. And then we are left with I, right? How do we find I? So if you go back and look at table A18, it gives you list inertias of different geometries. And I can tell you that it doesn't quite list this geometry where there's a sort of a hole inside it's like a box, there's a cutout, which is also like a box, like a thin section. And so you need to find the inertia from scratch. So let's do that. So I'll find I next. What we know so far is that if you have a box and it's solid, h b, then the inertia about this axis is b times h cube divided by 12. And this is from the appendix. Go to A18 and find the formula. So in order to find the inertia of something which looks like a hollow box, that's your outer layer. Let's try it 2 times. So we are trying to find the inertia of the hollow box as shown on the left. You can actually compose that box by taking in the outer box, which is solid now, and subtracting from it the inner box. And then the inertia of the composite piece here, let's call it I, equals the inertia of this piece minus the inertia of this piece. And this is something you probably have done before. It's not new. So let's put in the dimensions of the box, and we'll just compute the inertia from those dimensions. The height is 5. And the width is 3.25. So that'll be the same for the outer one. And the inner one, the height is, so the thickness is given as 3.25, no, 0.25. So pardon my figure, it doesn't really look equal, but the thickness is the same. It's called it T, and T is 0.25. Okay, so now we can find this dimension. It's going to be the height 5 minus 2 times the thickness, right? Because there's going to be thickness down and thickness up. So 5 minus 0.5, so it'd be 4.5. And in this dimension, the width is going to be, again, it's 3.25 minus 0.25 on the left, 0.25 on the right. So it's 3.25 minus 0.5. So that's 2.75. So the inertia is inertia of this piece, and we know that the dimensions are 5 and 3.25. So I'll just use this formula. That's the width. Height is 5 cube divided by 12 minus height of the piece on the right. So it's 4. Sorry, the width on the piece on the right. So 2.75 times 4.5 cube divided by 12. Okay, so I did the math on that. Comes out to be 12.97 inch raised to 4. Okay, I think we're all set to compute the moment now. Let's look at the formula we had written down. We have so sigma, well, sigma is known and I is known. So the formula is m equals sigma times I divided by y, and we've identified what y is and sigma is. So there. M equals sigma I divided by Y. Sigma, well, sigma max, so it's, I believe, 20 KSI, 20. Inertia is 12.97. The Y is Y max, it's 2.5. And then I get 103.8. So M is 103.8. So since we are dealing with IPS units, the units of M is going to be kip inch. Sigma was, so sigma, so SUT, yeah, it was in KSI. So since sigma was in KSI, your units for this is going to be kip, where kip, the K is kilo, so 10 raised to 3. And that's only because sigma was in KSI. Okay, so that completes part A. Next, we need to solve for radius of curvature. And we can write another formula from my notes from the previous class. So the formula is M divided by I equals E divided by R equals sigma divided by Y. So that sitting in there are really two equations because there are two equal to signs. We can combine any of those two equal to sign to get an equation. So you could use these two, or you could use these two. It's your choice. Let's just use the first one. So M divided by I equals E divided by R. And so 1 divided by R is M I, and M divided by EI. Okay, by the way, this is the radius of curvature. It is 1 divided by R. It's not R. R is the radius. Radius of curvature is the inverse of inverse of R. So now you can sub in. M is 103.8 kip inch. E is 10.6 times 10 raised to 6. And then I was computed as 12.97. So 1 divided by R equals, I get 110.4. 6. It's by the way 110.4 feet. So you can see that's a really, really large number, 110.4 feet. I mean, a normal human being is 6 feet tall or 5 feet tall. And this is like 20 times that. That's not the radius, it's the curvature. So if you want to find the radius, you do inverse of that. So 1 divided by 110.4. So you can see that the R is really small. Right? That will look right to me. Can you check this calculation? Yeah. Sure. So R is this, right? And the 1 divided by is a measure of how much it's curved. So if you have a flat line, like a plane, then R equal to infinity, right? The radius, the center of that circle is at infinity. So that 1 divided by R equals 1 divided by infinity is 0. So you can see it's perfectly flat. The moment you keep increasing R, you'll see it becomes curved. So that this gives you a sense of, this gives the 1 divided by r gives you a sense of the curvature. So for a beam, what you expect is it won't really bend that much, right? It will be slightly bent, because if it bends too much, then that's not a very strong structure, because just imagine seeing a bridge which is sagging by a large distance. So is there something wrong? So if 1 divided by r is such a large number, then r is very small. That doesn't look right. I think I did a calculation mistake here. I can quickly check this. Physically, it doesn't make sense. So 103.8, this should be KS. Points. No, I get it's not right. That should be a really small number. I get 7 point. Let me just check this. 103. Yeah, I get, my bad. So this should be 7.55 times 10 raised to -4. Right. So that makes sense now, because clearly the curvature should be very close to 0, right? In fact, the less the structure bends, the more safer you'll feel. Oh, it does have unit. I should have put that. It's inch inverse, right? Just the inverse of radius. So inch inverse in this case. This is 10.6, and this is 10 raised to 6. Any other questions? Okay, I like that you guys ask questions and try my best to answer them. Okay, so next, let's do another problem. And this, I think, takes it a little bit like the next level. This is slightly more complex than what we've seen before. The beam shown is acted upon by a moment M. So if the moment is given, determine the maximum tensile and compressive stress on the beam. So what we asked in this problem is find sigma tensile. So let's abbreviate that by sigma T, or sigma capital T, and sigma compressive, which is sigma C. Okay, so there's nothing new in terms of application of formula. It's the same formula. E divided by R. I'm just going to put this part, sigma divided. I'm going to, basically we'll need to use the maximum stress. Max. Okay, so in this question, M is given to us, it's 3 kilonewton meter. I is unknown. Sigma is clearly unknown. We need to solve for both sigma T and sigma C, and Y max is unknown. You know, two of those things which are unknown are based purely on geometry. So I is based on geometry, Y is based on geometry, and we are given the geometry of the T section B. So we can use the information from that figure, like this one, to figure out both those things. Okay, so I think first we need to solve for the neutral axis. If we don't solve for the neutral axis, we cannot compute y, right? And then unless we have the neutral axis, we again cannot compute inertia because the inertia is about the axis passing through the neutral axis. So the first thing is to compute the neutral axis. So compute the location of neutral axis. Okay, in other words, what we need to do is compute the geometric center. So we find the geometric center of the T section. So I'm going to redraw that section. Okay, and then put the dimensions on it. Okay, before we put the dimensions, when you compute the geometric center, you'll use this formula. Delta so some people like to use y prime for the geometric center. That'll be summation a times y divided by summation of a. That's the definition. So I need to break it down into individual areas whose centroid I know about, and then use that formula. So there are various ways to break this down. You can break it down this way. So there's this piece and this piece, and you can use that formula. The other way to do it is you can break it like this, and there's this piece, this piece, this piece, and then you can use the formula. No matter how you break it down, you will see that you get the same answer. Just seems like finding the centroid using 3 pieces is more work. So try to reduce it to as minimum pieces as possible. In this case, I'll just use those 2 pieces I drew earlier. Okay, so that's how we'll do it. This is 1, this is 2. Always choose an axis so that you can measure the distances from that axis, and you can choose any point. Some people like to choose here. Some people like to choose there. I just use this. Okay, but you can obviously choose some other point too. You'll get the same answer, but the answer will always be from the axis you chose. See, so if we call this y, I really don't need the x-axis. So this is 0. If you like, draw the x-axis this way, so that z points out of the plane of the paper, 0, 0. Okay, now we need to find the centroids of individual pieces. So the centroid of this piece, of piece 1, and the distance should be measured from the origin, is 10 mm, just from here. And then the centroid of the second piece, so you can see here, this is 40, so the centroid is at 20 from this cut. So it's going to be here. Okay, then I'll fill in the dimensions. 30, 20, 90. Okay, so here we go. Y bar equals. So I need to do area 1, y1 plus area 2, y2 divided by y1, so a1 plus a2. where ones and twos that represent those two rectangles I drew. So let's find the area for the first rectangle. So it's going to be 20 times 90. And then we need to find the distance of the centroid from the axis, sorry, from the origin we chose. That would be the center, that would be this point. It's 10 mm from the origin. So 10. Okay, next we need to find the area of the other rectangle. It has a length of, well, it has dimensions of, I think it's 40. So 40 times 30. And then the distance, again, the distance would be from the origin. So distance of the centroid is 20 plus this 20, so it's 40. Divided by the area. We already completed the 20 times 90 plus 40 times 30. Okay, so same thing I did here. So it comes out to be 22 mm. Okay, so you can plot that on this figure. Since this is 20, it's going to be slightly below the first rectangle. It's 22 millimeters from the origin. Coordinates are 0, 22. Okay, now let's find the inertia. And once I find the inertia, I'll use the inertia and this information to compute y max. So one piece of information I need for the inertia is, if I want to find the inertia of any thing about the y-axis, then it is b h, so b h cube divided by 12. That's the inertia about the centroid. If I want to find the inertia about a different axis, so let's say I want to find the inertia about not the center, but some axis at a distance of r from the centroid. This is the centroid, this is the centroid, and this is some different axis. So IC, this is IC. If you want to find IC bar, which is a different axis, then it's the inertia about C, about the centroid, plus area, which is the area of that rectangle, times the radius, not the radius, the distance from C to C prime, C bar squared. This is known as the parallel axis theorem. So I'll use this because in this case, the centroid does not pass through the centroid of the individual rectangles, right? It is 22 inches, which is not on the red dots I've shown. So I need to use the parallel axis theorem. Okay, so with that, let me now compute the inertia. So inertia, moment of inertia. Let's call that, let's call it G. About neutral axis, so point G. So for that, I need to find the inertia for 1 about G plus inertia of 2 about G. Rectangle. Okay, so let's do that individually. Okay, so first I'm going to use this formula here. Okay, so if I were to find the inertia about G for rectangle 1, I need to first find the inertia about the center of mass or centroid of the rectangle 1, which will be 1/12. B happens to be 90. H is the height of that rectangle, it's 20 cube, plus the area times the distance from G to the centroid of the first rectangle. So the area is 90 times 20. And then the distance between these 2 points and I need this distance. It's going to be 10 plus 2, I think it's 12. So it's going to be 12 square. So that comes from that formula for rectangle 1. But I'm not done yet. I need to find the inertia, moment of inertia for 2. So that would be, again, 1/12 times the width, which is 30, times the height, which is 40 cube, plus the area, which is 40 times 30, times the distance from G to the centroid. It's going to be this distance. So maybe it's 20 minus 2, I think it's 18. Right? Is it 18? That's what my guess is going to figure. Or is that wrong? So this is 20, and this distance is 2. This is 2 mm. So it's 20 minus 2, 18. Okay, so that comes out to be, check. Okay. So that answer is 868 times 10 raised to 4, 10 raised to 3 millimeter raised to 4, right? Because I used everything in millimeters. And then it might be in our best interest to convert that to meters by multiplying by 10 raised to negative 12, comes out to be 8.68 times 10 raised to negative 4 meter raised to 4. Okay, we're almost done. Now we found the inertia. We only need to find the right y in order to solve for the maximum tensile and compressive stress. So let's just take a look again at the way this moment is applied, because that will help us decide which side is compressive, which side is tensile. So if you back, you'll see that there's a moment this way, which means that the beam will bend like inverted U. So the top part is going to be under what? Tension. So there's going to be sigma T on top and has to be sigma C down. So all we need to do is find the distance from the neutral axis to the bottommost point to find sigma C, and find the distance from the centroid to the topmost point to find sigma T. So let's just do that. So the beam will bend something like this. Sigma tensile, sigma C. When you draw so we need to find this distance and of course this distance. So the distance of the centroid from the topmost layer, let's do that first. So distance from this point to all the way to the top is 2 mm plus 20. So it looks like it's 22. Okay, and then look at the other one. So it's a distance from this point all the way to the bottom. That's going to be 18 plus, I think, 20. So 38. That's right, 22 and 38. Again, sigma C, sigma T. So now, using that formula, sigma equals my divided by I. We'll have to use the formula in the following way. So sigma T is m, which is it's 3 kilonewton meters, so 3 times 10 raised to 3. The y would be 22 mm, which I can convert to meters, so 10 raised to negative 3, divided by inertia, which we already found. It's 8 point. Hold on. I incorrectly wrote this. This is 868. 8.68. I'm missing the decimal place. Incorrect. Negative 7. Just correct this. 8.68 10 raised to negative 7. 8.6. So plugging in the numbers, you get 76 MPa. And then sigma C, the same formula, except that you'd use a different y. What's this? So m is the same thing, 10 raised to 3. Now the y is 38 because the bottommost layer is in compression. So 38, 10 raised to negative 3. Divided by the inertia, it's the same, 8.68. Okay, and then plugging in the numbers gives me Well, I got 131.3 MPa.